BANYAGA and I will give you some sample problem for members.
Hello, my name is Errol ROSARIO and I will discuss about truss, methods of joints, and methods of sections. Trusses are one of the most common structures used in large-scale construction, but yet they are actually one of the simplest to analyze due to a couple basic assumptions. Number 1. Joints are pinned. Number 2. All members are two-forced. Number 3. All loading is applied to all joints. These assumptions are simplifications of most structures. Most loading is distributed along the length of the member, as opposed to just at the joints. Luckily, these assumptions are on the conservative side and can be assumed for basic analysis. For all truss member, the load in each member can only be applied at the two ends of each member. If a third load is applied to the member as shown in the right figure, then it cannot be a truss member. With only two forces on the member, they must be collinear to be in static equilibrium. Main concepts to remember are forces only act at the pin joints. Member forces are always in the direction of the member, and there are no moments in a member. There are two methods to actually solve for each member load: the method of joints and the method of sections. The method of joints examines each joint as an independent static structure. The summation of all forces acting on the joint must be equal to 0. Both member forces and external forces are applied to the joint, and then the force equilibrium equations are applied. For 2 dimensions, the equations are the summation of f of x is equal to the summation of f of y and is equal to 0. Since each joint must be in equilibrium, these two equations can be applied to each point. Generally, the support reaction should be determined first, and then the reaction joints should be solved. The joint sequence for solving can be important for multiple joints. For the methods of sections, the methods of sections splits the truss up into two or more parts and then applies both force and moment equilibrium equations. Because two or three dimensional sections are used instead of one-dimensional point, as with the method of joints, additional moment equations can be used to solve for truss member loads. The biggest benefit of this method is the ability to solve for member forces in the middle of the truss without solving for a large number of joints. First, the truss is split into two sections and all cut members are placed with an unknown member load. Make sure that only 3 members are cut for a two-dimensional truss. The unknown member force are then treated as external loads and can be determined. Remember to solve for the support loads first, since they will be needed in most problems to determine to cut member loads. The basic equations for each sections are summation of f of x is equal to summation of f of y and is equal to 0, and the summation of m of z is equal to 0. That's all for the truss, method of joints, and method of sections.
So for the sample problem, for the method of joints, determine the force and members AB, BD, BE, and DE of the whole roof truss shown, given that each angle is equal to 30 degrees. So what is required for us to solve our members AB, BD, BE, and DE. So our first step is to get the moment at H. So since it is in equilibrium, the moment is equal to 0. So the force acting on the truss, force A upward, so A multiplied by the distance by joint H is equal to 12 meters plus the distance, downward distances 2.7, 4.5, and 1.8. Since it is downward, that should be negative, so minus 2.7 kilonewton times the distance of 9 meters, and the other 4.5 times the distance 6 meters, and the last force 1.8 times the distance 3 meters, all equal to 0. So force A is equal to 4.725 kilonewton. So after getting the moment at joint H, you can solve the force at A. So let's solve the force at joint A. So this is the free body diagram at joint A, involving forces of members AB, BC, and A. So since we only need member AB, we can disregard AC since we don't have a value for it. So let's just have the summation of the forces along Y should be equal to 0 since it is equilibrium. So negative AB sine 30, AB is extended until third quadrant, plus the upward force of A, which we have computed earlier, 4.725 is equal to 0. So AB is equal to 9.45 kilonewton compression since AB is assigned as a compression at joint A. Next, let's now solve forces at joint B, and this includes members AB, BD, BC, and BE. So here, to let us solve the equation easily, we could rotate the given figure like this, and let's have AD as our x-axis for our free body diagram at joint B, and of course the perpendicular of it as our y-axis. So let's draw its free body diagram. So since we rotated it, our x-axis are members AB and BD, and let's assign them as a compression since we used AB in the previous solving for joint A as a compression too. So should look like there. From the given AB, BD, yes. Next for BC, so this angle here, the third quadrant. So let's just assign BC as a tension. From here, BC would be this, and BE, let's assign it as a compression. BE, BC, there. So since the angle in the figure is 30 degrees and we need this angle, so 30 plus 90 and 180 minus the two angles is equal to 60. So the angle between BD and BE is 60 degrees, and also from AB to BC is 60 degrees. There. Now let's solve for the summation of f of x should be equal to 0. So the forces acting along x are AB, since positive since it is going the right, BD is negative, BE, let's just extend BE up here, so this should be negative BE cosine 60, and BC downward, so negative BC cosine 60 is equal to 0. So for the summation of y, we have BE sine 60 and negative BC sine 60 equal to 0. So as you can see in the diagram, by inspection you can say that BC is equal to 2.7 kilonewton tension. So by inspection, BC is 2.7 kilonewton tension. So since we have a value for BC, we can now solve for BE from the equation of f of y. So from here, let's solve for BE. BE sine 60 minus our value for BC, 2.7 times sine 60 is equal to 0. So BE is now equal to our value for BA is 2.7 kilonewton positive, and B is assigned as a compression, so this is also a compression. Now for the equation of f of x, since you have a value for AB and BE and BC, we can now solve for BD. So AB is 9.45 minus BD minus the value for BE, 2.7 times cosine 60 minus the value for BC is 2.7 times cosine 60 is equal to 0. So the value for BD is equal to 60, 2.7, 60. This is 6.75 kilonewton, positive again. And BD is assigned as a compression, so this is also a compression. There, so we have now value for BD and BE. So let's check So lastly, let's solve for the member DE. So let's solve forces at joint D, which involves members BD, DF, and DE. D is the required member. So let's draw its free body diagram. Here. BD was assigned as a compression at joint D. So we will also assign it as a compression at joint D. So this will go this BD, and let's also assign member DF as a compression. DF both have 30 degrees with respect to x-axis, and member DE. So let's just assign this as a tension. There. So let's now solve for the summation of forces along x and y. So along x, let's just extend DF and BD, the second quadrant and the first quadrant. So BD cosine 30 minus DF cosine 30 is equal to 0. Since you have a value for BD, which is 6.75 kilonewton, let's just substitute that in this equation. 6.75 times cosine 30 minus DF cosine 30 is equal to 0. And DF is equal to DF is equal to 6.75 kilonewton compression. So now let's solve for the summation of y to solve for DE. So that's BD sine 30 plus DF sine 30 minus DE is equal to 0. Since you have value for BD and DF, let's substitute this to the equation. Sine 30 plus 6.75 sine 30 minus DE is equal to 0. So now the final value for DE is 6.75 positive. So since D is assigned as a tension, this should be tension. So there you go. Our values for AB, 9.45 kilonewton compression, and BE, 2.7 kilonewton compression, BD, 6.75 kilonewton compression, and DE, 6.75 kilonewton tension. Thank you.
So I am Charles Gabriel LLABAN from BSChE 3-1, and I'm here to discuss to you the method of sections. So to fully understand my example later, I'll give a brief concept about the method of sections. To start, the method of sections involves cutting off members. So you will use a section line to cut members. The section line will serve as the X-ray to view the forces inside each members, but there is a restriction. You should not exceed 3 members. Should not, take note, should not exceed 3 members at a time. The method of sections involves static equilibrium. So by equilibrium means that the summation of f of x, or the forces in x, is equal to 0. The summation of y, forces in y, is equal to 0, and the summation of moment is equal to 0. Moment is applicable in method of sections in solving forces. So here are the procedures in solving the forces using the method of sections. The first is determine the support reactions. You can do this, as I said a while ago, using a section line. You will cut the members using the section line. As you can see on step number 2, cut and draw. So you were given an illustration. You will cut it using a section line and draw the appropriate free body diagram. Then apply the 3 equations of equilibrium which was shown earlier. The summation of the forces in x is equal to 0, the summation of forces in y is equal to 0, and the summation of moment is equal to 0. So for the example, the problem is the truss in the illustration is pinned to the wall at point F and supported by a roller at point C. Calculate the force in members BC, BE, and DE. So this is the illustration. So you were asked to solve BC, BE, and DE. This is the one pinned at point F, and here is the roller at point C. So as you recall the procedure that I showed to you earlier, first is to determine the support reactions using a section line. So here is the section line. As you can see, I managed to follow the restriction 3 members at a time. I did not exceed. So determine the support reactions. Think, if the point F is removed, what will happen to the E? It will go over here. So to counter that force, the force in this must be in this direction to keep it in equilibrium. This also needs the force to be there to maintain equilibrium. And here at BC, the force must be in this direction to counter the force in DE or DF. So here is the triangle. 5, this one is 4 meters. So we need to solve for DE. In the problem, we need to solve BE, BC, and D. So I choose BE to be the first one to be solved. We need the measurement of this line. So I separated it from the given. This is 5, so this is 5 meters. This is 2 meters. So by Pythagorean theorem, we will get a value of square root of 29. Is the square root of 5 squared plus 2 squared is equal to square root of 25 plus 4 is equal to square root of 29. So we get the measurement of BE. Going back to the given, we need to solve for BE. We're given forces here. So to get the value of the force in BE, we must get the summation of forces at f of y. So it is in equilibrium. So it is equal to 0. The force of BE multiplied by its angle. So since it's in the force in y, it is sine times the angle. So what is the sine of this angle? It is opposite over hypotenuse, which is 5 over square root of 29. Since these two forces are pointing downward, let us subtract. Minus 60 minus 80 is equal to 0. By manipulating the equation, f dE times sine 5 over square root of 29 is equal to 60 plus 80. So FBE is 60 plus 80 over sine 5 over 29. As you calculate the answer, you will get 150.78 kilonewton. How about determining if it is tension or compression? Tension, if it is tension if it goes to the point and compression if it is away from the point. For the case of BE, it goes towards the point, so it is tension. Next is the force in BC. So we managed to solve BE. We will find BC and DE. Going back to the given, we will find BC. So here is BC. To get the force in BC, we need to find the moment in E. The summation of moment in E, since it is equilibrium, it is equal to 0. So here it is. Force times distance. Since we are finding BC, it is the force in BC multiplied by 5. The distance between BC and point E. Since 60 is and 80 is point are pointing downward, since BC is clockwise, it is positive. 80 and 60 are counterclockwise from point E. They are counterclockwise, so they are subtract. So minus 80, the distance from point A to E, this is 4 plus 2 is 6, so 80 times 6 minus 60, the distance of point B to E, which is 2. Manipulate the equation, we will get force in BC, which is 120 kilonewton. Go back to the illustration. BC is away from the point, so it is compression. So we got BC last but not the least, the force in DE. So to find the force in DE, we will get the moment in point D. So the summation of the moment in B is equal to 0 since it is in equilibrium. So the distance of force DE from B is 5. Since it is force times distance, so FDE by 5. Here is point B. The arrow points to the right. It is clockwise, so it's positive. Here 80, and the distance from B is 4. So since it is counterclockwise, point B, it is negative, so minus 80 multiplied by 4 is equal to 0. So transpose FDE is equal to 64 kilonewtons. Go back to the given to distinguish if it is tension or compression. So DE, it goes toward the point, so it is tension. So for our final answer, the force in DE is equal to 64 kilonewton. Tension, the force in BC is equal to 120 kilonewton. Tension, compression, and the force in BE, which is 150.78 kilonewton, and tension. So here are the final answers. So that ends our discussion about the method of sections.
Given a figure, we are assigned to determine the reaction at A, tension ED, and the force in member DC. Since ED is a tension, let's assign the force acting on point E is T, and in point A, the AY and the AX. We are assigning X as the distance of E from D, and the Y for the distance of D from the line AC. Using Sokotawa, y is equals to 5 sine 37 degrees. So we will get y is equals to 3 meters. And x is equals to 5 cosine 37 degrees. We will get x is equals to 4 meters. After getting x and y, he assigned D as the horizontal distance of D to C, and W as the length of member DC. From the whole figure, we can use the summation of moment at point A to determine the value of T. Since the summation of moment A is equals to 0, so 0 is equals to 100 times the distance 2 plus 800 times the distance 6 plus T times 6 times the 4 over 5. We will get T is equals to 1041.67 kilonewton. Since we have the tension, we can get now the AY by the summation of Fy equals to 0. So 0 is equals to negative 100 minus 800 plus AY plus T times 3 over 5. Substituting the value of T, we will get AY is equals to 275 kilonewton. Again, we can also use the moment at point E, since summation of moment at point E is equals to 0. So 0 is equals to 100 times the distance 2 plus 800 times the distance 6 minus the 6AX. So in this formula, we can determine the value of AX. We will get AX is equals to 833.33 kilonewton. From the figure of the FBD of member AC, we will use the summation of moment at point A. So the summation of moment at point A is equals to 0. So 0 is equal to 100 times the distance 2 plus 800 times the distance 6 minus force CD times 6 times 3 over the square root of 13. we will get FCD is equals to 1,002 kilonewton.